Hello, and welcome back to Learning to Program with Go, where we are walking through the fundamentals of programming while also covering the language features of Go. In today's video, we will cover the fundamentals of a program and how to store information. I came from a very low-tech high school that was behind in national education. As I was going into CS in college, I had several questions in regards to the terms of data and algorithms. I felt that these concepts were some great abstraction that I couldn't understand until I became smarter, but I slowly learned that there isn't much to uncover about what these terms mean. Google defines data as facts and statistics collected for reference or analysis, and in my own words, I define it as any information, whether it be numerical or qualitative, that can be used to describe an abstraction or concept or support such a description. In other terms, we can label the attributes of anything as data. Let's take a look at a person abstraction. A person has a name, age, eye color, and other attributes, all of which are data supporting the description of that person. We can even go further by saying every person has some geolocation if they have some device that tracks it, even though a geolocation isn't directly describing the person, but it still is data about the person. These aforementioned examples have a heavy influence of object-oriented programming, and object-oriented programming is an approach that is a great introduction into thinking about how abstract computers and programs are. In the last video, we created a string variable to hold the words "hello world" and later used what was stored in that variable to give to the toCaml function. This was our first introduction to how we can use stored information in our program during its execution, but unlike Python, we need to have assigned data types to our variables. Before we dive into all the variable data types that we can have, it's important to understand what a variable declaration is. To declare a variable means that you're declaring or saying that there is some container of data that is going to be used later in the program. So if I wanted a variable that's named message that's going to be of type string, it will be in the format of var, meaning variable, then the name of that variable, which is message at this time, and it's going to be of type string. And we use it later in our program on line 10, where we assign message equal to hello world. Variable initialization is similar to variable declaration, but the initialization of a variable is actually assigning a literal value to the variable. And you can only do variable initialization with inside a function. So I am inside the main function right here. And if I wanted to create a variable named x that's going to hold a particular number and it's already assigned to that variable, I can do x, then you do colon, equal sign, and then the literal value that you are going to place into it. We cannot do this outside of the function, but if you are wanting to have some sort of container outside of the function, then you can use constant declaration. If we were wanting to do constant declaration instead, it means that the variable, which it technically isn't a variable anymore, it's a constant, this container or the value that it contains will not change. So this is a good practice if you're trying to not assign values that don't change and represent some sort of higher abstraction. So let's say that we had to use the number pi in our program, or really just the first 3 digits of pi. So I can go ahead and say const, and then pi is equal to 3.14. And then later on in my program, I can go ahead and print out pi by just passing it in. Let's go ahead and save and run, and we get 3.1 printed to the console. Again, these constants up above cannot change. They're intended to represent other abstractions in our program. If we go back to my definition of data, where I say that it can be numerical or qualitative, that directly translates to the categories of data types that we can have. Go follows Java's notion of primitive and reference types. Go has 5 subtypes of pre-declared types: int, float, bools, strings, and runes. And starting with ints, an int stores a whole number. So we can represent someone's age, the number of pixels on a screen, or how many days there are in a month with an int. Go has several integral types with a range of how many bytes we can store to hold its value. In the smaller range, we have the int8, which its smallest value can be -128 and its max is 127. Its unsigned version has a minimum value of 0 and a max of 255. Since memory is so cheap nowadays, you do not always need to use int 8 or uint 8. It's just idiomatic to use the int data type to represent potentially any negative or positive whole numbers. If you find yourself needing to extremely optimize the speed or memory performance of your application, then that's when you should look into the other integral data types. If you find yourself needing to store numbers with decimals, then you can use the float32 or float64. But note that these data types are not super precise in terms of their precision. If I have a variable named x that starts at 1.01 and a variable I that starts at 0.01, and I run a loop while x is less than 1.4, what I do is I go ahead and add I to the value of x continuously until x is greater than or equal to 1.4, and it also prints out the value of x. So what would you think that the final value of x would be once it's greater than or equal to 1.4? Well, let's find out. Let's go ahead and run this. And what you see is that we start at 1.01 as expected. We add 0.01 to it and we get 1.02. And we continue to do this. But as you can see, right after we're done at 1.12 and we increment to 1.13, we actually get a whole bunch of extra decimals and then an additional 1 right here. We increment to 1.14, but we still have that 1 on the tail end. And we can see that it slowly grows out of precision the more times we go ahead and increment this number, so much that we get all the way up to 0.3 at the end. Now this is the fallback of floating point numbers. Computers cannot exactly store 1.01 or 1.02. There's actually a whole bunch of extra bits that are storing other numbers, but for the meantime it will just show that there are zeros until you continuously add upon them. Now, I'm not going to get into the details of why computers store numbers or decimals this way. If you want more information on that, you can go check out the IEEE 754 specification, and you can figure out how that works on your own research. But at the end of the day, you should not be using float32s or float64s to represent currency or other concepts where precision is critical. You may have heard that computers are all made up of ones and zeros, but these ones and zeros actually represent electrical signals. Go represents this binary value as Bool, coined after George Bool, who developed Boolean algebra. Go's Boolean values can only hold one of two values, true or false. We can use this concept in programs to control its flow, but that's for another video. We can either assign the literal value of true or false to a Bool variable, or a Bool variable can be assigned to the result of a Boolean expression. For example, I have a print statement here that is printing the result of 1 less than 20. 1 is less than 20, so if we go ahead and run this program, we're going to see true is printed to the console. If we go ahead and change this to 20 is less than 20, make sure we save and run the program again, we're going to get false. 20 is not less than 20, it's the same number. If we wanted to show this with variables, we can go ahead and create a variable named x, set it equal to 1, and we can have another variable that's set equal to 2, and let's print out their value. So I can say x is less than y, and if we print this out here, we get true because 1 is less than 2. And if we also just want to store it in its own variable, we can go ahead and say we'll have b represent Boolean, and we'll say is equal to x less than y. And then we can replace the statement right here with b, make sure we save it, and we get the same result. Lastly, Go has strings, which represent a series of characters like hello world, or singular characters such as h, or the empty string. If you're wanting to represent only a single character, it is better to use the Rune data type. So for instance, I can go ahead and create a Rune named R1, and we can set it equal to h that it is above. And again, you're going to get this red squiggly here if you have not used R1 yet. So I'll go ahead and do a print line of this Rune R1, and let's go ahead and print out the output of this program. So the first print statement is going to be assigned to hello world, then we'll get an h, we'll get an empty string, and then we'll get Rune1 printed to the console. Run this, and we see that we get hello world printed like we said, then h, which is also another string, the empty string, and then you would have thought since a Rune is just a single character, then it'll print that single character. But actually what is happening is that it's printing the code point of h. So h actually secretly represents 104, and you'll find out that the Rune data type is actually an alias for int32. We will go into this in more depth in future videos. But all that you need to know is that strings carry a series of characters that we can represent as like plain text. If I could go ahead and give you a hint of research on why runes are an alias for int32, I encourage you to go ahead and look up ASCII tables. To synthesize all the information that I've given you in this video, let's create a simple program that will go ahead and print some of the data about me. So we'll say that I learned the number pi in 5th grade. So I'll create a grade variable that's equal to 5. We'll also say that my name is equal to Holton. And then lastly, we'll print out if my age is under a certain threshold. So my variable is going to be called age under 45, and we'll say 23 less than 45. Now let's go ahead and put some print statements together here. So I'll do a format.printf, and I'm going to go ahead and introduce you to the printf function here a little bit, but we'll make this into another video at some point. So we'll say %s learned I, we'll put that in parentheses, do a %f in grade, and then a %d. He is now age %d, and then put in that new line there. Again, this will all be explained in another video of how this works, but the short and sweet of it is that this will go ahead and map to the first argument after the string that is a string. So what we're going to do here is go ahead and place the name variable here. So name will eventually be put into the string that gets printed out here. And so %f will try to map to a double or a float value. That is the second argument that comes after the string. So we'll be placing pi here. Grade comes next, and then age comes very last. Or wait, I did not do age. We'll say, is he under 45 question mark? And then we'll do a %b, and then we can use age under 45. Let's hope this all works out here. Save and do a go run. And it looks like we got Colton learned pi, which is 3.14 in grade 5. Is he under 45 question mark? And then we get %b bool equals true. If you come from another programming language where printf is common, usually %b is used to represent Boolean values. But in Go, you should actually be using t, because as you can see, b did not come out correctly here in our printf statement. So let's change that to a t, save it, let's rerun this program, and then we get Colton learned pi 3.14 in grade 5. Is he under 45? True. So there we have it. You got to learn all about variable declarations, initialization, data types, and how to write a program to represent some of this data. Thank you for sticking around to the end of this video. If you learned something, then I encourage that you like and subscribe to the video, as I'm going to continue putting out more Learning Go videos, and I hope to see you in the next one.